friends, welcome back. In the previous session, we evaluate the derivative of functions directly using the definition. In this session, we describe various techniques of differentiation involving basic rules of differentiation. This will help us to differentiate functions without having to apply the definition each time. We also describe chain rule, a formula that expresses the derivative of a composition f composition G in terms of the derivative of f and G. Derivatives of powers, multiple, sum and difference. The first rule of differentiation is that the derivative of every constant function is 0. Rule 1, derivative of a constant is 0. If c is a constant, then d upon dx of c is 0. We prove this as follows. With f of x equal to c, f of x plus h equal to c also, and f prime x equal to limit of f of x plus h minus f of x upon h as h approaches 0, which is equal to limit of c minus c upon h as h approaches 0, which is equal to limit of 0 upon h as h approaches 0, which is equal to 0. In particular, d upon dx of 8 equal to 0, d upon dx of negative 1 upon 2 equal to 0, d upon dx of square root of 3 equal to 0. Rule 2, power rule for positive integers. If n is a positive integer, then d upon dx of x power n is n x power n minus 1. We prove this as follows. If f of x equal to x power n, then f of x plus h equal to x plus h whole power n. F of x plus h minus f of x upon h equal to x plus h whole power n minus x power n upon h. Since n is a positive integer, taking a equal to x plus h and b equal to x, a power n minus b power n equal to a minus b into a power n minus 1 plus a power n minus 2 into b plus etc. plus a b power n minus 2 plus b power n minus 1. Help us to simplify the above, and we obtain f of x plus h minus f of x upon h equal to h times x plus h to the power n minus 1 plus x plus h to the power n minus 2 into x plus etc. plus x plus h into x power n minus 2 plus x power n minus 1 upon h, which is equal to x plus h to the power n minus 1 plus x plus h to the power n minus 2 into x plus etc. plus x plus h into x power n minus 2 plus x power n minus 1. N terms each with the limit x power n minus 1 as h approaches 0. Hence, d upon dx of x power n equal to limit of f of x plus h minus f of x upon h as h approaches 0, which is equal to limit of x plus h to the power n minus 1 as h approaches 0 plus limit of x plus h to the power n minus 2 into x as h approaches 0 plus etc. plus limit of x plus h into x power n minus 2 as h approaches 0 plus limit of power n minus 1 h approaches 0 by some rule of limit function, which is equal to x power n minus 1 plus x power n minus 1 plus etc. plus x power n minus 1 n terms, which is equal to n times x power n minus 1. In particular, d upon dx of x square equal to 2x. The next rule says that when a differentiable function is multiplied by a constant, its derivatives multiply the same constant. Rule 3, the constant multiple rule of differentiation. If f is a differentiable function of x and c is a constant, then d upon dx of c times f of x equal to c times d upon dx of f of x. We prove this as follows. D upon dx of cf of x equal to limit of cf of x plus h minus cf of x upon h as h approaches 0 using the definition of derivative with the cf in place of f, which is equal to limit of cf of x plus h minus cf of x upon h as h approaches 0 since Cf of x equal to C times f of x, which is equal to C times limit of f of x plus h minus f of x upon h as h approaches 0 by constant multiple rule of limit of function, which is equal to C times f prime x. In particular, using the constant multiple rule of differentiation and the power rule for positive integer, we obtain if n is a positive integer, then d upon dx of C x power n equal to C times n x power n minus 1. As another example, since d upon dx of x square equal to 2x, d upon dx of 3x square equal to 3 times d upon dx of x square equal to 6x. Geometrical meaning of the last example is this. Since the derivative of x square is 2x and that of 3x square is 6s, it follows that slope at each point ordered by x naught, g of x naught in the graph of g of x equal to 3x square is 3 times the slope at the point ordered by x naught, f of x naught of the graph of f of x equal to x square. The next rule says that the derivative of the sum of two differentiable function is the sum of their derivatives. Rule 4, the sum rule. If f and g are differentiable function of x, then their sum f plus g is differentiable at every point where f and g are both differentiable. At such points, d upon dx of f of x plus g of x equal to d upon dx of f of x plus d upon dx of g of x. We prove this as follows. We apply the definition of derivative to the function f of x plus g of x. D upon dx of f of x plus g of x equal to limit of f of x plus h plus g of x plus h minus f of x plus g of x upon h as h approaches 0, which is equal to limit of f of x plus h minus f of x upon h plus g of x plus h minus g of x upon h as h approaches 0 by an algebraic rearrangement, which is equal to limit of f of x plus h minus f of x upon h as h approaches 0 plus limit of g of x plus h minus g of x upon h as h approaches 0 by the sum rule of limit of function, which is equal to df upon dx plus dg upon dx. The sum rule also extends to sum of finitely many functions. If f1, f2 etc. fn are differentiable at x, then so is f1 plus f2 plus etc. plus fn, and d upon dx of f1 plus f2 plus etc. plus fn equal to dfn upon dx plus df2 upon dx plus etc. dfn upon dx. We prove the statement using mathematical induction. We recall mathematical induction. Let n naught be a natural number and let p of n be a statement for each natural number n greater than or equal to n naught. Suppose that first one, the statement p of n naught is true, and second one, for all k greater than or equal to n naught, if p of k is true, then p of k plus 1 is true. Then the statement p of n is true for all n greater than or equal to n naught. By the sum rule, we have d upon dx of f1 plus f2 equal to df1 upon dx plus df2 upon dx. Hence, the statement is true for n equal to n naught equal to 2. This is step 1 of the induction proof. Step 2 is to show that if the statement is true for any positive integer n equal to k, where k greater than or equal to 2, then it is also true for n equal to k plus 1. So, suppose that d upon dx of f1 plus f2 plus etc. fk equal to df1 upon dx plus df2 upon dx plus etc. plus dfk upon dx, equation number 1. Then d upon dx of f1 plus f2 plus etc. plus fk plus 1 equal to d upon dx of f1 plus f2 plus etc. plus fk plus dfk plus 1 upon dx. By the sum rule with the f equal to f1 plus f2 plus etc. plus fk and g equal to fk plus 1, which is equal to df1 upon dx plus df2 upon dx plus etc. plus dfk upon dx plus dfk plus 1 upon dx. With these steps verified, the mathematical induction principle now guarantees the sum rule for every integer n greater than or equal to 2. Rule 5, the difference rule. The difference rule says that the derivative of a difference of differentiable function is the difference of their derivatives. D upon dx of f of x minus g of x equal to d upon dx of f of x minus d upon dx of g of x. D upon dx of f of x minus g of x equal to d upon dx of f of x plus negative 1 times g of x, which is equal to d upon dx of f of x plus negative 1 times d upon dx of g of x, combining the sum rule with the constant multiple rule, which is equal to d upon dx of f of x minus d upon dx of g of x. By applying the various rules mentioned above, we can find the derivative of any polynomial. Hence, every polynomial is differentiable. As an example, let us find the derivative of y equal to x cube plus 4 upon 3 x square minus 5x plus 1. dy upon dx equal to d upon dx of x cube plus d upon dx of 4 upon 3 x square minus d upon dx of 5x plus d upon dx of 1, which is equal to 3x square plus 4 upon 3 times 2x minus 5 plus 0, which is equal to 3x square plus 8 upon 3x minus 5. Differentiation of product of two differentiable function. Using the sum rule of limit of function, limit of f of x plus g of x as x approaches c equal to limit of f of x as x approaches c plus limit of g of x as x approaches c. We have obtained the sum rule of differentiation d upon dx of f of x plus g of x equal to d upon dx of f of x plus d upon dx of g of x. But from the product rule of limits of functions, limit of f of x into g of x as x approaches c is limit of f of x as x approaches c into limit of g of x as x approaches c. Never expect a result of the form d upon dx of f of x into g of x equal to d upon dx of f of x into d upon dx of g of x. That is, while the derivative of the sum of two function is the sum of their derivative, the derivative of the product of two function is not the product of their derivatives. For instance, d upon dx of x into x equal to d upon dx of x square equal to 2x, while d upon dx of x into d upon dx of x equal to 1 into 1 equal to 1. Thus, the situation is different in the case of derivative of product of two functions from that of addition and difference of functions. The derivative of a product of two function is the sum of two product, as we now explain. Rule 6, the product rule. If f and g are differentiable at x, then so is their product f g, and d upon dx of f of x into g of x equal to f of x into d upon dx of g of x plus g of x into d upon dx of f of x. Now, let us prove the product rule. D upon dx of f g equal to limit of f of x plus h into g of x plus h minus f of x into g of x upon h as h approaches 0. To change this fraction into an equivalent one that contain difference quotients for the derivatives of f and g, we subtract and add f of x plus h into g of x in the numerator. Then d upon dx of f g equal to limit of f of x plus h into g of x plus h minus f of x plus h into g of x plus f of x plus h into g of x minus f of x into g of x upon h as h approaches 0, which is equal to limit of f of x plus h into g of x plus h minus g of x upon h plus g of x into f of x plus h minus f of x upon h as h approaches 0, which is equal to limit of f of x plus h as h approaches 0 into limit of g of x plus h minus g of x upon h as h approaches 0 plus g of x into limit of f of x plus h minus f of x upon h as h approaches 0. Now, limit of f of x plus h as h approaches 0 is f of x, because f being differentiable at x and is continuous at x. The two fraction approaches the values of dg upon dx at x and df upon dx at x. In short, d upon dx of f of x into g of x equal to f of x into d upon dx of g of x plus g of x into d upon dx of f of x. As an example, let us find the derivative of y equal to x square plus 1 into x cube plus 3. From the product rule with f of x equal to x square plus 1 and g of x equal to x cube plus 3, we find d upon dx of x square plus 1 into x cube plus 3, which is equal to x square plus 1 into 3x square plus x cube plus 3 into 2x, which is equal to 3x raised to 4 plus 3x square plus 2x raised to 4 plus 6x, which is equal to 5x raised to 4 plus 3x square plus 6x. Differentiation of quotient of two differentiable function. Just as the derivative of the product of two differentiable function is not the product of their derivatives, the derivative of the quotient of two function is not the quotient of their derivatives. What happens instead of this? Rule 7, the quotient rule. If f and g are differentiable at x and g of x not equal to 0, then the quotient f upon g is differentiable at x and d upon dx of f of x upon g of x equal to g of x into d upon dx of f of x minus f of x into d upon dx of g of x upon g of x whole square. Simply writing, d upon dx of f upon g equal to g f prime minus f g prime upon g square. Now, we prove the quotient rule. D upon dx of f upon g equal to limit of f of x plus h upon g of x plus h minus f of x upon g of x upon h as h approaches 0, which is equal to limit of g of x into f of x plus h minus f of x into g of x plus h upon h into g of x plus h into g of x as h approaches 0. To change the last fraction into an equivalent one that consists the difference quotients of the derivative of f and g, we subtract and add g of x into f of x in the numerator, then we will get d upon dx of f upon g equal to limit of g of x into f of x plus h minus g of x into f of x plus g of x into f of x minus f of x into g of x plus h upon h into g of x plus h into g of x as h approaches 0, which is equal to g of x into f of x plus h minus f of x upon h minus f of x into g of x plus h minus g of x upon h upon g of x plus h into g of x as h approaches 0. Now, taking the limit in the numerator and denominator give the quotient rule. To illustrate the quotient rule, let us find the derivative of h of x equal to x square minus 1 upon x square plus 1. We apply the quotient rule with f of x equal to x square minus 1 and g of x equal to x square plus 1. d upon dx of h of x equal to x square plus 1 into 2x minus x square minus 1 into 2x upon x square plus 1 whole square, which is equal to 2x cube plus 2x minus 2x cube plus 2x upon x square plus 1 whole square, which is equal to 4x upon x square plus 1 whole square. The power rule for negative integers. The power rule for negative integers is same as the rule for positive integers. Rule 8, power rule for negative integers. If n is a negative integer and x not equal to 0, then d upon dx of x power n equal to n x power n minus 1. The proof uses the quotient rule in a clever way. If n is a negative integer, then n equal to negative m, where m is a positive integer. Hence, x power n equal to x power negative m equal to 1 upon x power m, and d upon dx of x power n equal to d upon dx of 1 upon x power m, which is equal to x power m into d upon dx of 1 minus 1 into d upon dx of x power m upon x power m whole square using quotient rule with f of x equal to 1 and g of x equal to x power m, which is equal to 0 minus m x power m minus 1 upon x raised to 2m. Since m greater than 0, d upon dx of x power m equal to m x power m minus 1, and since the derivative of constant 1 is 0, which is equal to negative m x power negative m minus 1, which is equal to n x power n minus 1, since negative m equal to n. For example, d upon dx of 1 upon x equal to d upon dx of x power negative 1, which is equal to negative 1 times x power negative 2, which is equal to negative 1 upon x square. This agrees with the results in the previous session. D upon dx of 4 upon x cube equal to 4 times d upon dx of x to the power negative 3, applying the constant multiple rule, which is equal to 4 times negative 3 x power negative 4, which is equal to negative 12 upon x raised to 4. Let us use the rules mentioned in this session to find the equation of the tangent to the curve y equal to x plus 2 upon x at the point ordered pair 1 3. The slope of the curve is dy upon dx equal to d upon dx of x plus 2 times d upon dx of 1 upon x, which is equal to 1 plus 2 times negative 1 upon x square, which is equal to 1 minus 2 upon x square. The slope at x equal to 1 is dy upon dx at x equal to 1 equal to 1 minus 2 upon x square at x equal to 1 equal to 1 minus 2 equal to negative 1. The line through ordered pair 1 3 with the slope m equal to negative 1 is given by the point slope equation y minus 3 equal to negative 1 times x minus 1, that is y equal to negative x plus 1 plus 3, that is y equal to negative x plus 4. The power rule for real numbers. So far we have discussed the power rule for positive and negative integers. In the previous session, we have seen that d upon dx of square root of x equal to 1 upon 2 square root of x, that is d upon dx of x power 1 by 2 equal to 1 upon 2 x power negative 1 upon 2, which is equal to 1 upon 2 x power 1 upon 2 minus 1. This shows that the power rule is valid for the rational number n equal to 1 upon 2 as well. In fact, it can be shown that this formula holds for any real exponent. We state this more general result for our use now. Rule 9, extended power rule. If r is any real number, then d upon dx of x power r equal to r x power r minus 1. That is, to differentiate a power function, decrease the constant exponent by 1 and multiply the resulting power function by the original exponent. As an example, d upon dx of cube root of x equal to d upon dx of x power 1 upon 3, which is equal to 1 upon 3 x power minus 2 upon 3, which is equal to 1 upon 3 cube root of x square. Choosing which rule to use. The choice of which rule is used in solving a differentiation problem can make a difference in how much work you have to do. Here is an example. Rather than using the quotient rule to find the derivative of y equal to x minus 1 into x square minus 2x upon x raised to 4, expand the numerator y equal to x minus 1 into x square minus 2x upon x power 4 equal to x cube minus 3x square plus 2x upon x power 4. Then actual division by x power 4 gives y equal to x power minus 1 minus 3x power minus 2 plus 2x power minus 3. Then using the sum and power rule, we obtain dy upon dx equal to negative x power negative 2 minus 3 times negative 2 x power negative 3 plus 2 times negative 3 x power negative 4, which is equal to negative 1 upon x square plus 6 upon x cube minus 6 upon x power 4. Second and higher order derivatives. The derivative f prime equal to d upon dx of f is the first derivative, first order derivative of f, with respect to x. This derivative may itself be a differentiable function of x. If so, its derivative, second derivative of f equal to d upon dx of f prime equal to d upon dx of f, which is equal to d square upon dx square of f, is called the second derivative or second order derivative of f with respect to x. If f2 is differentiable, its derivative f3 equal to d upon dx of f2 equal to d cube upon dx cube of f is the third derivative or third order derivative of f with respect to x. The names continue as you imagine with fn equal to d upon dx of f power n minus 1, denoting the nth or nth order derivative of f with respect to x for any positive integer n. Also, we note that fn of x equal to dn upon dx power n of f of x. The first four derivative of f of x equal to x cube minus 3x square plus 2r, first derivative f prime x equal to 3x square minus 6x, second derivative f2 of x equal to 6x minus 6, third derivative f3 of x equal to 6 and fourth derivative f4 of x equal to 0. Given function has derivatives of all orders, the fourth and latter derivatives all being 0. Derivatives of compositions, the chain rule. Suppose you have travelled to your workplace in your car, which gets 18 km per liter of petrol. The number of kilometers you can travel in your car without refueling is a function of the number of liters of petrol you have in the petrol tank. Mathematically, if y is the number of kilometer you can travel and u is the number of liters of petrol initially in the petrol tank, then y is a function of u given by y equal to f of u equal to 18u. The number u liters of petrol initially in the petrol tank is a function of the amount of money you spend for the petrol. If 1 liter petrol costs rupees 60, then each rupee you spend will give you 1 upon 60 of liters of petrol. So, if x is the number of rupees you spend on petrol, the number u of liters of petrol initially in the petrol tank is u equal to g of x equal to 1 upon 60 of x. Now, by applying the constant multiple rule, we obtain f prime u equal to dy upon du equal to d upon du of 18u equal to 18 km per liter. That is 18 km per liter of petrol is the rate at which your mileage changes with respect to the amount of petrol you use. Also, by applying the constant multiple rule, we obtain g prime of x equal to du upon dx equal to d upon dx of 1 upon 60 into x, which is equal to 1 upon 60 liters per rupees. We note that the number y of kilometer you can travel is also a function of the number x of rupees you spend for petrol. The fact is expressible as the composition of function y equal to f of u equal to f of g of x. You might be interested in how many kilometers you can travel per rupee, which is dy upon dx. Intuition suggests that a rate of change multiply in this case. So, dy upon dx equal to dy upon du into du upon dx, that is equal to 18 km upon 1 liter into 1 liter upon 60 rupees equal to 0.3 km per rupee. The following theorem formalize the preceding ideas. Theorem: the chain rule for function of one variable. If g is differentiable at x and f is differentiable at g of x, then the composition f composition g is differentiable at x with its derivative is given by f composition g prime x equal to f prime g of x into g prime x. Alternatively, if y equal to f of g of x and u equal to g of x, then y equal to f of u is differentiable composite function of x and dy upon dx equal to dy upon du into du upon dx, equation number 1. As an illustration, we use the chain rule to evaluate d upon dx of 1 upon x cube plus 2x minus 3. If we take u equal to x cube plus 2x minus 3, then d upon dx of 1 upon x cube plus 2x minus 3 equal to d upon dx of x cube plus 2x minus 3 to the power negative 1, which is equal to d upon dx of u to the power negative 1, which is equal to d upon du of u to the power negative 1 into du upon dx, which is equal to negative u to the power negative 2 du upon dx, which is equal to negative x cube plus 2x minus 3 to the power negative 2 d upon dx of x cube plus 2x minus 3, which is equal to negative x cube plus 2x minus 3 to the power negative 2 into 3x square plus 2, which is equal to negative 3x square plus 2 upon x cube plus 2x minus 3 whole square. Let us summarize the session. In this session, we describe various techniques of differentiation and use them to differentiate function. We also describe chain rule, a formula that expresses the derivative of a composition f composition G in terms of the derivative of f and G. Hope you enjoy the session. See you next time. Until then,